what if the smooth, continuous space separating you from your device right now is, well, a complete illusion?
Yeah, that is essentially the million-dollar question we're facing right now.
Right, because think about it. You sit down in a lecture hall for your first upper-level general relativity class.
Oh, I remember that day well.
Exactly. And the professor walks in, points to the chalkboard, and draws this beautifully curved, perfectly stretched canvas.
The classic rubber sheet analogy, right?
Yeah, the rubber sheet. And you're taught that the universe is this smooth manifold, completely continuous, infinitely divisible.
Which works great for the macroscopic world, sure.
Right, you spend hours, I mean, literally weeks, wrestling with tensor calculus and Christoffel symbols under the strict assumption that space-time is this unbroken fabric.
Right.
But what if we've been looking at a low-resolution image this entire time, and someone finally just handed us the magnifying glass so we can actually see the pixels?
Well, the truth is, we are hitting a massive wall in theoretical physics right now, precisely because we've been treating that low-res image as the fundamental truth.
Like it breaks down. Right.
Exactly. The continuous equations of general relativity, they just break down completely at the quantum level.
You get infinities everywhere.
Right. They produce infinities. They fail miserably inside black holes. So to fix that, we are kind of being forced to look at a cosmological landscape that is inherently structural.
Like pixelated almost.
Yeah, pixelated. A universe that isn't just this passive, empty void, but a highly complex, self-organizing network.
Okay, so for you listening right now, especially if you're an undergrad whose brain is currently just saturated with Einstein field equations and smooth manifolds, we are asking you to temporarily throw all of that out the window.
Just for an hour.
Yeah, just for this deep dive. Because today, we are diving into a radical paradigm-shifting framework called Quantum Truss Spacetime, or QTS.
Proposed by Uncle Ted, right.
Right. And our mission today is to break down the core thesis of this model, translate its discrete mathematical action into something that makes, intuitive physical sense.
And critically, look at how this moves humanity from being passive observers of gravity to, well, active space-time architects.
Spacetime Architects, I love that voice. It's a staggering ambition.
It really is. I mean, we're talking about fundamentally redefining what space actually is.
Moving away from the container model.
Exactly. Moving from the idea of a passive container where things just happen to a dynamic, computable medium that can actually be engineered.
So let's start with the most basic physical geometry of this new model, because it just completely flips the script on standard GR.
It really does. In QTS, general relativity isn't a fundamental description of reality at all.
Right. It's just the coarse-grained, hydrodynamic limit of a microscopic network made of what the paper calls entanglement struts.
Yes, entanglement struts.
And I want to lean into that hydrodynamic analogy for a second, because in your intro physics courses, you learn about fluid dynamics.
Right, the Navier-Stokes equation?
Exactly. Navier-Stokes describes water as a perfectly continuous flowing medium. And it works brilliantly, right?
Oh, absolutely. If you're designing submarines or plumbing systems, it's perfect.
Right, but we know that if you zoom in on a glass of water, that continuous fluid doesn't actually exist.
No, you find discrete, interacting H2O molecules.
Right, so the smoothness of the water is an emergent property.
Yes, an illusion created by averaging out all the chaotic interactions of trillions of tiny, discrete particles over a very large volume.
And QTS is saying we have to apply this exact same logic to space-time itself.
Exactly.
Right.
Which means the curvature we study in GR, the Ricci scalar that dictates how planets orbit stars.
The thing we spend semesters calculating.
Right. That isn't a fundamental property of the universe at all. Curvature is emergent.
Wow. Okay, so in standard GR, we treat the metric tensor as the fundamental field.
We do. But in quantum truss spacetime, the metric tensor is just the macroscopic consequence of the collective state of this underlying microscopic truss.
So space is not something that exists in the lattice. Space is the lattice.
Exactly. Space is the lattice.
Okay, but if space is the lattice, and obviously it's not made of H2O molecules, we have to define what these components actually are.
Right. We can't just say struts and move on.
Yeah, the framework uses the specific term entanglement struts. So connecting the dots here, we aren't talking about physical rods of matter, like steel or something.
Definitely not. We are talking about quantum information.
Okay.
The struts must be localized densities of quantum entanglement that link fundamental nodes together.
So the nodes of this lattice are discrete degrees of freedom.
Yes, and the struts connecting them are the physical manifestations of entanglement.
I see. So the geometry of the space, like the literal distance between 2 points, is dictated by the strength and density of that entanglement network.
Exactly. And this forces us to completely reevaluate what entanglement actually is.
Right, because usually we think of it as just, Einstein's spooky action at a distance.
Right, something happening between two particles that already exist inside space.
But here, entanglement is the thread that actually sews the space together in the first place.
Yes. Without the entanglement, there is no distance. There is no space.
That immediately puts us in an engineering mindset, doesn't it? I mean, if space-time has a physical network structure, it acts like a material medium.
And material mediums have physical engineering principles. We can analyze them.
Right. We should be able to look at the structural integrity of this cosmic truss.
Just like civil engineering.
Exactly. In civil engineering, a steel bridge has load-bearing properties. You have variables like the tensile strength of the steel, the rigidity of the joints, things like that.
Right, and the QTS framework introduces two fundamental variables for the spacetime truss to mirror exactly that.
Okay, what are they?
Stiffness, denoted by the Greek letter kappa, and strut strength, denoted by gamma.
Kappa and gamma. Okay, let's break these down because I assume these are the foundation of the entire theory.
They absolutely are. Let's look at stiffness first, kappa. This variable acts as the coupling constant for the gravitational degrees of freedom in the lattice.
Okay, so to map this to what you are studying in GR right now, kappa is analogous to the inverse of Newton's gravitational constant, right? Like 1 over g.
Precisely. It dictates how resistant the lattice is to geometric deformation.
Okay, so if I have a region of space-time with a very high kappa, that lattice is essentially made of titanium.
Right. It takes an immense amount of energy or mass to warp it even a little bit.
And a low kappa would mean the space-time is incredibly pliable, like a trampoline.
Exactly. Now, the second variable, strut strength, or gamma, this governs the entanglement entropy cost of the geometry.
Entanglement entropy cost, meaning what exactly?
Well, to maintain a specific configuration of entanglement, to keep the nodes connected in a specific shape, it requires energy.
Oh, okay.
Gamma represents the structural integrity of the struts themselves. It basically tells us the energetic price the universe has to pay to maintain its local geometry.
I love this. We are literally applying civil engineering to the cosmos.
We really are. Think about it. A bridge truss is designed to distribute physical loads, right? Tension and compression from the weight of all the cars.
Sure.
The space-time truss is distributing energy momentum.
Oh, man. So when a massive object like a star exists in space, it doesn't just warp a smooth, passive canvas.
No, the mass, the stress energy tensor you calculate in GR, it acts as a localized physical load on those lattice nodes.
And the lattice responds to that load by redistributing the entanglement entropy across the struts to minimize the stress.
Exactly. And that microscopic redistribution, that manifests macroscopically as the local space-time curvature we perceive as gravity.
That is just, it sounds incredible on paper. But I have to point out a massive engineering bottleneck that Uncle Ted actually highlights in the text.
Oh, the energy requirements.
Yeah. If our goal is to become space-time architects and actively manipulate this truss, say, to build a warp drive or traversable wormhole, we immediately run into the Riccio-Turing equation.
The bane of all exotic space-time engineers.
Right. In tensor calculus, the Riccio-Turing equation basically tells us how gravity focuses matter. And to create significant exotic geometric deformation, the math says we need to violate classical energy conditions.
We need negative energy densities.
Exactly. And our current real-world approximations for negative energy are, well, they're abysmal.
We have the Casimir effect.
Yeah, the Casimir effect, where we place two uncharged conductive plates just micrometers apart in a vacuum.
Right, and because they restrict the wavelengths of the vacuum fluctuations that can fit between them.
The space outside the plates has a higher energy density than the space inside, creating a tiny attractive force.
But the scale of that negative energy is just infinitesimally small.
Right. To warp space-time enough to create a macroscopic lens or a real anomaly, we would need the negative energy equivalent of like a Jupiter-sized mass.
Which we obviously don't have.
So how do we actually tune this lattice without requiring the energy output of an entire star?
Well, this is where QTS really innovates. It bypasses the brute force requirement of the Riccio-Turing equation through a mechanism called active lattice tuning.
Active lattice tuning. How does that work?
Instead of relying on raw bulk mass or, hypothetical oceans of negative energy, active lattice tuning proposes the precise injection of high-energy quantum coherent states into highly localized regions of the lattice.
Oh, I see. So we aren't trying to bend the entire bridge with sheer weight.
Exactly. You're taking a microscopic, highly calibrated laser, metaphorically speaking, and heating up a very specific joint in the truss to change its local tension.
Wow. Because the lattice naturally redistributes entanglement entropy in response to localized stress anyway.
Right. So by injecting coherent quantum states, you exert a targeted force on the lattice nodes. You are essentially hacking the variables locally.
Artificially modifying gamma and kappa in a microscopic region.
Yes. And the lattice reacts to this artificial entropy redistribution by curving, exactly as if a massive object were present, but without actually requiring the mass.
You are tricking the geometry into bending by altering the entanglement cost directly.
Precisely.
That is brilliant. But, for a physics student, analogies only go so far. A theory without mathematical formulation is just philosophy.
We need the math.
We need the math. We need to look at how kappa and gamma actually generate the geometry using the discrete action equation of the QTS model,
Right. So in smooth, continuous math, like what you do in class, we use the Einstein-Hilbert action.
which is an integral over the spacetime manifold.
Exactly. But since QTS is discrete, we obviously can't use a continuous integral.
Right, because there's no continuous space to integrate over.
So we must replace the continuous integral with a discrete sum over the fundamental geometric building blocks of the network.
Okay, and the paper defines this QTS action, S_QTS, as a sum over all the plaquettes in the lattice.
Plaquettes.
So if we are dealing with a lattice, a complex web of interconnected nodes, a plaquette must be the smallest possible closed loop you can make by following the struts.
Exactly. It's the fundamental polygon of the grid.
Okay.
The action equation has two primary terms inside that sum.
Let's take them one by one.
Okay, the first term dictates the gravitational degrees of freedom. It is the stiffness, kappa, multiplied by the area of the claquette, multiplied by the discrete Ricci scalar, denoted as R sub p.
Okay, I really want to break down R sub p here, because this is where the geometry actually happens.
Go for it.
In GR, the normal Ricci scalar is a continuous measure of how a small volume deviates from flat Euclidean space.
You're right.
But in a discrete lattice, you can't do that. You have to calculate curvature using reg calculus.
Yes, reg calculus, you look at the deficit angle.
Exactly, the deficit angle.
Mhm.
So imagine you take a vector and parallel transport it, basically. You walk it carefully around the edges of that plaquette.
Right, keeping it parallel to itself.
If the space is perfectly flat, the vector comes back, pointing in the exact same direction it started.
But if the space is curved, the vector comes back pointing at a slightly different angle.
And that difference is the deficit angle, delta sub p.
Exactly. And the discrete Ricci scalar, R sub p, is simply calculated by taking twice that deficit angle and dividing it by the area of the plaquette.
So it is a purely geometric, microscopic measure of curvature.
Yes. So the first term of our action is essentially evaluating three things. How stiff is the lattice loop? How big is its area? And what is its intrinsic deficit angle?
Okay, that makes perfect sense. And the second term of the action accounts for the energy cost.
Right.
It is the strut strength, gamma, multiplied by the sum of the entanglement entropy of all the individual struts that make up that specific loop.
Yes, exactly. So when you combine that structural geometry term with the entanglement energy term, the lattice action defines the total dynamical state of the spacetime web.
So if I were coding a simulation of this to model the node dynamics, I'd be setting up a Hamiltonian operator, h hat.
You would, and the text outlines the Hamiltonian for a specific node utilizing a holonomy operator around the strut.
Denoted as x hat sub e. Right.
Right. And an entanglement entropy operator, S hat sub e.
Okay, so the holonomy operator is what mathematically performs that parallel transport around the loop we just talked about, checking for the deficit angle.
Exactly. You are essentially doing geometric programming at that point.
That's wild. But wait, the moment you write down a discrete Hamiltonian for spacetime, you run into a huge problem, right? The most persistent critique of any lattice model.
The violation of Lorentz invariance.
Right, because Lorentz invariance is the absolute bedrock of special relativity.
It states that the laws of physics are the same for all observers, regardless of their velocity or direction.
Right, the universe has no preferred direction. But if spacetime is built on a lattice, a literal grid, it inherently has a grain, like a piece of wood.
Yes, the anisotropy problem.
Right. A particle moving diagonally across the grid would experience a subtly different geometry than a particle moving straight along the struts.
Which would imply a rigid, anisotropic universe, which completely contradicts relativity.
So how does the QTS model survive that?
Well, Uncle Ted relies on a very powerful mathematical framework for this. Renormalization group, or RG flow.
Okay, RG flow.
We have to look at the flow equation for kappa, beta of kappa, which dictates how the stiffness of the lattice behaves at different scales.
Okay, so in condensed matter physics, when you use Wilsonian renormalization, you are essentially integrating out the high-energy microscopic fluctuations.
Right, to see how the bulk material behaves at a macroscopic level.
Yeah, like zooming out washes out the atomic lattice of a crystal to give you the smooth thermodynamic properties of a solid block of metal.
And the exact same mathematical machinery applies to the spacetime truss.
Really?
Yes. The RG flow equation demonstrates that as you scale up from the Planck length to macroscopic distances, the lattice becomes increasingly stiffer and more uniform.
Ah, okay.
The discrete, grainy fluctuations of the individual struts are systematically suppressed as you zoom out.
So the Lorentz violations are what particle physicists would call irrelevant operators.
Exactly. At the microscopic scale, they are highly active, but as you flow to the macroscopic infrared limit, the scale of atoms, humans, and planets, those violations decay to zero.
The lattice variations average out so perfectly that the geometry becomes mathematically indistinguishable from a smooth, directionless, continuous manifold.
The lattice effectively hides its own discrete nature. And this is tied deeply to a phase state analogy for the universe.
Oh, I was just thinking about that because tuning kappa in the Hamiltonian is exactly like tuning temperature in a thermodynamic simulation.
It is. Think about what happens if kappa is too low.
If it's too low, the structural integrity of the truss vanishes. It melts into a chaotic, high-entropy quantum gas where geometry itself just dissolves.
Right. Distance and time lose all meaning. It's a topological soup.
But conversely, if kappa is too high, the entire universe freezes into a hyper-rigid, non-relativistic crystal.
Exactly. Gravity ceases to be dynamic. Matter cannot move.
So gravity, the flexible, dynamic space-time we actually inhabit, only exists in this razor-thin Goldilocks zone.
Yes. It sits at a critical phase transition point where kappa and gamma balance perfectly, allowing the lattice to behave as a liquid-like computable medium.
We live entirely on the knife edge of that phase transition.
We do.
Which is thrilling, honestly, but it also raises a pretty terrifying concern.
What's that?
Well, if space-time is this pliable, liquid-like computational medium, and we now theoretically have the math to tune it using high-energy coherent states, what happens when we push too hard?
Ah, the causality problem.
Yeah. If a spacetime architect decides to aggressively manipulate the local speed of information, attempting to create a closed, time-like time machine, what prevents them from just shattering causality?
Right, we have to shift from the math of creation to the math of self-preservation.
Exactly. Because the classical defense of causality relies on the chronology protection conjecture, right? Championed by Stephen Hawking.
Yes. The classical assumption in GR is that any attempt to bend space-time into a time loop will cause vacuum fluctuations to circle the loop infinitely.
Building up infinite energy density.
Right. This results in vacuum polarization or catastrophic vacuum decay, which would instantly obliterate the anomaly.
And likely the surrounding solar system with it before the time machine could even form.
Yeah.
It's like a universal kill switch. Like, oh, you tried to break causality, so I'm deleting this entire sector of the galaxy.
It is an incredibly violent theoretical mechanism, but QTS offers a much more elegant solution.
Graceful degradation, I think the paper called it.
Yes, graceful degradation, driven by a self-healing property inherent to the discrete dynamics of the lattice.
Okay, let's look at the mechanism for that self-healing. Because we established earlier that the Hamiltonian includes an entanglement entropy term, right? The strut strength gamma multiplied by the entropy.
Yes.
And the paper says this term isn't just an energy cost calculator.
Yeah.
It functions as a restorative elastic force, a stability feedback mechanism.
Exactly. The space-time truss is not infinitely pliable. It possesses a strict elastic limit coded directly into its fundamental action.
The circuit breaker effect.
We term this the circuit breaker effect, yes.
So walk me through what happens. Let's say I try to build a time machine in the QTS framework. I set up my superconducting coils, I start aggressively tuning the lattice, trying to bend the geometry into a closed time-like curve. What actually happens?
As your local geometry approaches that paradoxical causal anomaly, The local entanglement entropy is forced into extreme, highly stressed configurations.
Okay.
And at the precise boundary where the anomaly would form, the system undergoes a sudden phase transition. The localized stiffness, that variable kappa we discussed, effectively skyrockets toward infinity.
Oh, well, that makes perfect sense. It's like a Chinese finger trap.
Yes, or a reactive, non-Newtonian fluid in a suspension system.
Right. The harder and faster you try to force the universe into an illegal paradoxical geometry, the harder the universe pushes back.
The lattice responds to the extreme stress by becoming infinitely rigid at that specific microscopic location. It creates an insurmountable energy barrier against any further deformation.
So you literally cannot force the stress into a paradox, because the geometry itself petrifies before the violation can occur.
Exactly. It locks the struts into a safe state.
The universe engineers itself to prevent us from breaking reality. I love that so much. We aren't going to accidentally trigger a vacuum decay that wipes out the universe. We're just going to hit an infinite wall of stiffness.
The circuit breaker trips.
That's amazing.
And it significantly alters the risk assessment for future spacetime engineering. The system is mathematically proven to be inherently stable against our worst theoretical mistakes.
Which is comforting, honestly.
Yeah.
But look, this is all beautiful mathematics and built-in paradox protection. For the undergrads listening, though, a theory is completely meaningless if it isn't falsifiable.
Absolutely true.
How do we test a discrete quantum truss model today? Because we can't exactly point the James Webb Space Telescope at a patch of empty space and just take a macro photo of an entanglement strut.
Falsifiability is exactly where QTS separates itself from pure string theory or, loop quantum gravity philosophy. The framework provides a clear quantitative signature that can be tested right now.
Right now, against the null hypothesis of continuous general relativity.
Yes, using existing data sets from the LIGO and Virgo observatories.
Ah, okay, gravitational waves. Ripples in the fabric of spacetime caused by merging black holes or neutron stars.
Exactly. Think about how a gravitational wave propagates. In standard GR, as a wave travels through continuous space, its propagation is perfectly smooth.
Right, because the medium is continuous.
But if space is fundamentally a discrete lattice, that wave is actually traversing a microscopic interconnected grid.
Like in solid-state physics, when a wave travels through a discrete crystal lattice-like sound moving through a diamond, it experiences dispersion.
Exactly. The higher frequencies of the wave interact differently with the physical spacing of the atoms than the lower frequencies do.
They scatter.
Yes. And that exact dispersion relation applies to gravitational waves in QTS.
Okay, so the wave's interaction with the microscopic nodes and struts causes a fraction of its high-frequency energy to scatter or reflect.
Precisely. And the Hamiltonian predicts this will manifest as a highly specific flicker, or a trailing echo, behind the primary gravitational wave signal.
The lattice echo.
The lattice echo.
But practically speaking, how does an astronomer looking at a LIGO readout actually spot that? I mean, the strain data from LIGO is incredibly noisy.
It is very noisy, yes.
How do you distinguish a literal truck driving down a highway a mile from the detector from the fundamental pixelation of the universe?
Right. It's a huge challenge. The paper proposes a rigorous mock data challenge utilizing Bayesian inference to solve this. You are correct. The signal-to-noise ratio for any single event is far too low.
So you can't just look at one black hole merger and see the pixelation.
No. However, the scattering wouldn't be random noise. Because the underlying lattice has a uniform physical scale, expected to be near the Planck length, the lattice echo will possess a consistent resonant harmonic signature.
Dictated entirely by kappa and gamma.
Exactly.
Oh, I see. So instrumental noise from a truck or a seismic tremor, that's random and localized. But this lattice flicker is a property of the medium itself.
Therefore, it must be universally consistent.
Right. Whether the wave comes from a binary black hole merger 3 billion light-years away or a nearby neutron-star collision, the wave is traveling through the identical structural medium.
Exactly. So by statistically cross-correlating hundreds or thousands of recorded wave events using advanced Bayesian models, the random, instrumental, and astrophysical noise will eventually cancel out.
But the systematic flicker caused by the lattice discreteness will compound.
Yes, eventually shifting the statistical likelihood decisively in favor of a discrete geometry.
That is a brilliant way to test it. But assuming the mock data challenge succeeds, assuming we find the lattice echo and prove that GR is just a low-resolution approximation observation isn't the end game here.
Not at all.
The framework gives us a mandate to become spacetime architects. We need to transition from deep space astronomy to active spacetime engineering.
And the source material actually outlines a Lattice laboratory roadmap to test this in a controlled lab setting.
The roadmap is divided into 3 distinct stages of experimental progression. Right, let's go through them. We have high-precision quantum metrology, synthetic physics simulation, and finally, localized structural manipulation.
Right, so let's look at stage 1, high-precision interferometry.
The goal here is to detect jitter in the lattice, but what is the actual physical mechanism we're looking for?
Well, we want to bring the search for the lattice from macroscopic astrophysical events down onto a controlled optical bench.
Okay.
Stage 1 utilizes dual interferometer setups. You shoot highly coherent light packets along a vacuum path while intentionally generating high-energy, chaotic quantum particle fluctuations directly adjacent to that path.
Okay, wait. If the QTS model is accurate, those high-energy particle fluctuations aren't just happening in an empty void. Their mass-energy dynamics are actively jostling the entanglement struts of the local lattice.
Exactly. This localized stress on the truss causes an incredibly rapid microscopic breathing or jitter in the local geometry.
The space itself vibrates.
The space vibrates. And this vibration alters the physical distance the light must travel by a fraction of an atom's width.
Which manifests as microscopic variations in the arrival times of the coherent light packets at the detector.
Yes, we are actively measuring the elasticity of the local truss in real time.
It's like measuring the structural sway of a suspension bridge by shooting a laser across it while someone jumps up and down on the middle span.
That is a perfect analogy.
Wow. Okay, so that brings us to stage 2. And for any physics undergrad listening, if you're looking for a thesis topic that will absolutely dominate the next 50 years, this is where you need to focus.
Absolutely.
Stage 2 is synthetic lattice creation using Rydberg atom arrays. Now, I know what a Rydberg atom is. It's an atom excited to a very high principal quantum number, meaning its outermost electron is orbiting at a massive distance from the nucleus.
Right.
But why are they the perfect tool for simulating a quantum spacetime?
Well, because of that massive electron orbit, Rydberg atoms are hypersensitive to external fields. And more importantly, they exhibit incredibly strong long-range dipole interactions.
Right.
They can interact and entangle with each other over distances of several micrometers. In the quantum realm, that is a vast distance.
So they act as highly programmable quantum nodes. You can use optical tweezers to arrange a grid of hundreds of individual rubidium atoms into any 2-dimensional or 3-dimensional array you want.
Yes. We can use these arrays to build a physical scale model simulation of the quantum truss.
Oh, wow.
We map the QTS Hamiltonian directly onto the physical properties of the atoms. The tunable dipole interaction strength between adjacent atoms perfectly simulates our stiffness variable, kappa.
And the internal states of the atoms, whether they are in a ground state or a specific Rydberg state, simulate the strut strength and entanglement entropy, gamma.
Precisely. You are physically coding the discrete action of the universe into an artificial grid of atoms.
And once that synthetic spacetime is built, we can actually test the circuit breaker.
We can.
We can watch information tunnel through this synthetic geometry. And we can intentionally crank up the laser driving the interactions to force the synthetic lattice into the equivalent of a gravitational singularity or a closed time-like curve.
We can map the exact energy thresholds where the synthetic circuit breaker triggers. We can watch as the atomic array undergoes a phase transition to infinite stiffness, locking up to protect its internal causal structure.
So we can master the elasticity of the Hamiltonian safely on a lab bench before we ever attempt to warp actual reality.
Exactly. Which leads directly into stage 3, localized curvature induction.
The actual transition to spacetime architecture.
Yes.
Stage 3 involves searching for microscopic gravitational anomalies around high-energy superconducting coils. Now, why superconducting coils specifically?
Well, if we are going to attempt active lattice tuning, injecting those high-energy quantum coherent states to exert targeted force on the lattice nodes, superconducting coils are currently our most viable macroscopic source of dense, controlled quantum coherence.
Because the electrons in a superconductor form Cooper pairs, merging into a single macroscopic quantum state.
Right. The goal is to see if the intense manipulation of entanglement entropy generated by the magnetic and quantum fields of the coils can force the surrounding spatial lattice to redistribute its struts.
We are looking for a measurable warping of the gravitational field caused not by the physical mass of the coils, but by the direct manipulation of the QTS variables.
Exactly. And if we can generate measurable gravity without mass, we unlock applications that completely redefine human civilization.
The paper specifically outlines gravitational refractive lensing based on Fermat's principle of least time.
Yes.
And we usually apply Fermat's principle to optics, right? When light travels from air into water or glass, it slows down because the refractive index of the medium changes. The light bends to take the path of least time.
Right, but in QTS, we are talking about applying that to gravity.
Because spacetime is a material lattice, it possesses an effective refractive index.
Yes. In a normal vacuum, that index is uniform. But if we can use our superconducting coils to establish localized gradients in the entanglement strength, if we can artificially vary the stiffness, kappa, across a region of space, we are physically altering the refractive index of the vacuum itself.
We are building a lens made of pure space.
Exactly. Light, or even other gravitational waves, entering this engineered zone will bend according to Fermat's principle, but the curvature is completely dictated by our tuning equipment.
We could create static, massive gravitational lenses in orbit, capable of focusing light from the edge of the observable universe with a clarity that physical mirror telescopes could just never achieve.
You just dial a knob to adjust the lattice tension and the lens focuses or defocuses.
That is mind-blowing.
And beyond observation, there is the potential for geometric storage. This is a monumental leap for data architecture and topological quantum computing.
Right, because quantum computers today struggle immensely with decoherence. The quantum states are so fragile that a stray photon or a slight temperature shift causes them to collapse, destroying the data.
But if we can map information directly into the topological structure of the spacetime lattice, if data is encoded into the localized entanglement entropy of the geometry itself, it becomes fundamentally immune to environmental decoherence.
Because the data isn't a particle sitting in space, waiting to be bumped by thermal noise.
No.
The data is the shape of the space. You are carving memory into the fundamental fabric of reality.
It is the ultimate endpoint of computation, space-time memory.
This entire deep dive represents such a profound paradigm shift. I mean, we've taken the smooth, passive canvas of general relativity and revealed it as a coarse-grained illusion.
It's a completely new way of seeing the universe.
The universe is a computational, programmable medium governed by stiffness, strut strength, and discrete Hamiltonians.
We are shifting from being creatures who simply inhabit a space subject to its immutable laws to becoming system administrators of the cosmic truss.
System administrator.
We are learning the programming language of reality, preparing to navigate, tune, and modify the structure itself.
So for the undergrads listening, you aren't just learning tensor calculus to describe what the universe is. You are learning the syntax for what the universe can become.
Well said.
But before you head back to your next physics lecture, I want to leave you with one final, provocative puzzle to chew on. We explored the universe's circuit breaker today, right? The way the lattice stiffness rockets to infinity to prevent causal paradoxes.
Right.
But QTS also implies that the speed of light, c, is not a hard fundamental ceiling imposed by God. It is simply a property of the lattice's current baseline configuration.
Exactly. It's just a variable.
So here is the question. What happens when we successfully manipulate the truss? If a future spacetime architect manages to engineer a localized bubble where they artificially suppress the stiffness and manipulate the strut strength, could information propagate faster than light within that bubble?
It's a terrifying and thrilling thought.
Can we actually rewrite the local rules of physics, breaking the cosmic speed limit entirely? Or will the universe's underlying circuit breaker always outsmart us, freezing the struts before we can truly break free? We finally discovered that the universe is a programmable web. The real question is, what happens when we hit enter on our first line of code?